Hi. So in this video I'm going to add something that I have lectured on from time to time in the past, but which is not in the handbook. So it's kind of been one of those things that I add on that maybe I haven't included yet. And you may have noticed, hopefully you noticed, that it's really pretty strange that we spend a lot of time in economics talking about what makes demand shift and what makes supply shift. And then we talk about policy shifts and macro, the Fed changes interest rates or the Congress changes taxes. And then you get into an advanced macro class and I throw the whole thing out the window and I start doing time series. And it's a univariate time series. The only thing that's in there is real GDP, except it seems to fit really well. That's kind of a weird thing. How can time series actually work? Again, most of you start out doing cross-sectional work, and if you think about what you do in the spreadsheet class or in the econometrics class or in decision modeling, you're always kind of finding relationship of one variable to another, and is this variable significant or not significant? Is the effect worthwhile, and so on. And then you get into macro and we do something completely different, and yet it seems to actually work better. How is that possible? Well, what I've done here is written up the simple math that you can actually run through and follow. It's only about a page and a half, about 10 equations or so. Okay, so it's useful to ask how can a time series model like an ARI 1-1 in log levels actually forecast something like the US economy fairly well? Um, I don't want to talk about the fact that it can. I've already demonstrated that in the handbook. I want to talk about why it's even possible at a theoretical level or a philosophical level. This is huge this year when we've got COVID-19 around because I've been pulling this COVID-19 data off the internet in class and online since spring break. And I've been showing that it can be fit pretty well by time series as well, and yet I don't know much about epidemic behavior, and neither do you. But the time series somehow does seem to know that before we even get there. How can that possibly work? Okay, so there actually is like a philosophical and methodological theory of causality that has been worked out by scientists and philosophers over the last 150 years or so. Um, and it has kind of all come together in econometrics maybe since the late 1960s with the work of Clive Granger. He won a Nobel Prize about 15 years ago for advances in time series. Um, but underlying all that is these theories of causality and a couple things that have come um, down to us through the philosophy is one, okay, excuse me, highlighting the wrong paragraph there, is that the cause has to precede the effect, that there has to be some sort of temporal ordering, that the cause is in the past, the effect is happening now, or the cause is happening now and the effect is in the future. Now, we're talking about time periods in class, and yeah, we might be talking about annual data or quarterly data or whatever, but this would have to work even at the microscopic level. So this is the sort of thing that physicists are also thinking about when they do stuff like particle acceleration, about how they're going to cause something to happen by running one particle into another, and the past has to precede the future. Okay, in terms of math and econometrics and regressions, that means that a causal relationship has to be an equation like this, that x causes y because beta is non-zero, and x causes y because x is in the past and y is in the future. Now, I've put that in linear form. Causality doesn't have to be linear, but of course it's easier to think about it as it is. And I've also made it stochastic. Now, remember that that word means a number of different things. And way back when I first introduced this in the classroom, I said stochastic trend maybe ought to be a word that we hyphenate instead of having two words. But stochastic really just means there's an error term. There's some unexplainable shock that's showing up in the data that we can't explain. It's a basic principle of statistics, right? Okay. Second idea is that causal relationships have to be triangular and I've shown that in the table below by shading it. So I have the causes going down the columns here, creating these effects on the left. So it's okay if past x causes current y. That's a legitimate causal relationship. It's okay if past x causes, excuse me, I said current y, I meant current x. Past x can cause current x. Past x can also cause current y. That's fine. That's in fact the equation that I showed up here. Okay. Past y can cause past current y down here, but past y cannot cause current x. Okay. Now that means that I've got 3 cells shaded is okay and 1 shaded is not okay. And if you think about it, what's going on here it's saying that if x causes y, y can't also cause x. Okay? At some level, the causality has to be one way. Now it's possible to say that past x causes current y, which then causes future x, and that would be kind of a feedback possibility, but it always requires the passage of time from the one to the other. That's perfectly reasonable. We just have to make this table that much bigger. Okay? All right, so if we combine the idea of temporal ordering and triangularity, it means that a very simple, in fact, the simplest causal system that we might write out that's stochastic would look like these two equations here. Okay, so in the first one, this is a repeat of what's above. Past x causes current y, and there's random noise. And in the bottom one, past x also causes current x, and there's some random noise in that as well. Now, you've probably gotten used to in this chapter, the handbook, of shifting equations backwards and forwards by time and rearranging them and resubstituting them. So that's all that I'm going to do here. It's just an exercise that I have not done before in front of you. So we're going to take this bottom equation right here, this one, and we're going to shift it back one period to right here. Okay, pretty basic thing that we did in the classroom a couple times in early March. Okay, and not surprisingly, the next thing I'm going to do is substitute in the right-hand side of this equation into the top equation here where I have xt minus 1. Okay, that again, simple algebraic substitution. That goes down to the next equation at the top of the next page. And I've got the whole thing written out there. Okay, now I am not going to simplify this at this point. I could simplify this and gather terms. I don't really want to. Okay, I can go and do what I need to without simplifying that. Okay, so now I'm going to go back to the original of the exact same equation. So that's this one right here. And I'm going to shift it back one period, excuse me. Going to shift it back to the original of this equation. Shift this one and shift that one back one period as well. So I'm going to get yt minus 1 equals alpha plus beta xt minus 2 plus epsilon t minus 1 right there. So that's this equation shifted backwards by one period. Okay. Now, even if I have a causal relationship here, that doesn't mean that I can't rearrange the pieces of the equation. That's algebraic and it's always okay. So I'm going to get the xt minus 2 over on the left-hand side like so. So you might call this in an algebra class, you might say solving for xt minus 2. Okay, that's not really what I'm doing here, but that might be the language that you would use. Okay, so most of the other terms go in the numerator, and the beta that's on the xt minus 2 ends up in the denominator when we divide through by it. And you can probably imagine I've got an xt minus 2 here and an xt minus 2 here. So I'm going to take the right-hand side of this equation and substitute it in right there in this equation. And that's what I do right here. Okay, so the yt comes down, the alpha comes down, the beta comes down, and right in the middle here in brackets, I have the right-hand side of this equation, and everything else is just copied down. Okay, it's a bit messy, and I could simplify this quite a bit, but I don't really need to simplify it to get to my essential point. My essential point is, if you look at this equation, the x's are all gone. All we have now is current y and lagged y and parameters and errors. The parameters are Greek letters and the errors are Greek letters. And in my handbook, the Greek letters are indicating things that you might estimate, but you can't choose. You don't observe those things. The X's and Y's are things that you observe or that a policymaker might choose. So it's nonlinear, it's messy, but here's the thing. That is an autoregression. That is a regression of y, or excuse me, if I estimated this, excuse me, if I estimated that equation, the equation itself isn't an autoregression, the estimate of it is an autoregression. I've got on the left-hand side current y, and the only variable on the right-hand side is lagged y. Okay, so this is an AR1. This is case 3. It's a more complex nonlinear version of case 3, but it is case 3 or case 4. Okay, and it turns out that if I pop back up here, if I make these equations more complex, more lags, more interaction and whatnot, more variables, I would get something down here that's more complex. But the basic idea is that a two equation system where everything is autoregressive can be collapsed into a one equation system that's autoregressive. Okay, I misspoke here. A two equation causal system that is not autoregressive, because this is not autoregressive here. I've got two different variables, so that prefix auto for self doesn't apply here, can be collapsed into something that is an equation in one variable and its lag. So that is an autoregression. This is huge. Okay, this is a stunning insight into the way that variables express themselves through time. Okay, we have a simple demonstration here that a causal system can be expressed as an autoregression, and it does readily extend to situations with more lags and more variables. As long as you've got temporal ordering and you've got triangularity somewhere in your system, you can collapse everything down into an autoregression. And this tells us why autoregressions fit as well as they do. It's because putting that lag in there is a way of putting in everything else that might be important to explaining why without having to know what everything else actually is. So it's implicitly picking up all of these causal relationships that maybe we know or don't know or can measure or can't measure. They're all in there already. They're kind of baked in. And because they're already in there, the autoregression actually kind of puts an upper bound on our ability to explain the data with a better structural model of causality. Okay, it basically has pinned down for us how predictable y is, no matter what we throw in on the right-hand side. Okay, so the idea that the ARI 1.1 models, like case 5 in the book, end up with a standard error in the range of something like 3% of GDP is indicative that GDP is inherently quite unpredictable, that it is doing its own thing, and that we're never going to be able to get a decent handle on how it behaves. That doesn't mean that we can't control it a little bit. That doesn't mean that we can't have policy that moves GDP up or down in a way that's maybe desirable to us. But it is telling us that most of what we are seeing most of the time is random noise rather than intentional behavior on the part of policymakers. If you had me back in principles, one of the things I emphasized from the first week of class is that policymakers are the ones telling us how important their policies are. But if their policies were really that good and all powerful, they'd never lose elections. And yet they lose elections all the time. And of course, people always want to claim power and eliminate elections because they know they might lose. This is all, as I said, baked into these autoregressions that we have. And with COVID-19, this means that an autoregression of some degree of complexity, maybe not the simple one that explains GDP, should be able to model things like cases and deaths per country fairly readily and fairly accurately without you and I knowing a whole lot about epidemiology or disease spread or social distancing or anything like that. Pretty cool, huh? All right, I will see you in another video. Bye.